Okay, this is the homework for gravitation. In this figure, four masses are at the corners of a sphere with an edge of length 20 centimeters. That means that this distance is 0.2 meters. The masses of the spheres are as labeled. Express the gravitational force on the fifth mass, which is in the middle. That's this mass is m, at the center of the square in vector notation, and then also what is the magnitude and direction of the force on this mass. So first, let's just label the forces. I'm going to call this mass 1, mass 2, mass 3, and then mass 4. So the first thing I want to recognize is that the force on this mass, which I'll call F1, is identical in magnitude to the force on this mass, F4. So F1 has the same magnitude as F4. And because of that, I can get rid of both of these, because they cancel one another out. They're equal in magnitude but opposite in direction. And then I can also draw F2, which is in this direction, and then F3, which is in this direction. And notice that I've drawn F3 smaller. It actually turns out that F3, because this mass is half the size of mass 2, F3 is going to be half the magnitude of F2. Now let's calculate F2. I'm just going to calculate the magnitude. That's G m2 m over r squared, where r is the distance between mass 2 and the central mass. So let's clean this up a little bit. And then I'll show you how to find that distance. So I want to know what is the distance from here up to here. I can draw a triangle here. And I know that this distance is 0.1 meters. This distance is 0.1 meters. And so r then, which is this distance, r will equal the square root of 0.1 squared plus 0.1 squared. Pythagorean theorem. And that's equal to the square root of 0.02, which is 0.14, but I'm just going to keep it like that for now. Okay, I'll show you why in just a second. All right, now let's go and calculate F2. G is 6.67, 10 to the minus 11. And I have my masses 3 grams, which is 0.003 kilograms, and then my mass in the center is 2 grams, 0.002 kilograms, divided by my distance, which is 0.02, or rather my distance is the square root of 0.02, but then I'm squaring that because it's r squared. And then if I do that, works out to be 2 times 10 to the minus 14 newtons. All right, now I also want to calculate what is the force due to this particle on this mass. But as I've already said, the only difference is going to be this number, and it's going to be half the value here. So F3 is going to be 1/2 the magnitude of F2. So F2 was 2 times 10 to the minus 14. This is going to be 1 times 10 to the minus 14 newtons. All right, so now I have that. I can draw my free body diagram. It's going to be pretty simple. You'll see this force was 2 times 10 to the minus 14 newtons, and then this force is 1 times 10 to the minus 14 newtons. And here, just for a moment, I'm going to draw my axes, my x-axis like that and my y-axis like this. And what that allows me to do is I can just go ahead and subtract those two vectors, and I can redraw that as just one vector at 1 times 10 to the minus 14 newtons. I've just subtracted this number from this number because they're opposite in direction. It's like they lie along the axis, so I can just subtract them arithmetically, just take the difference between them. And then because this is an equilateral or is a square, I know that this angle is 45 degrees. So there's my magnitude and there's my direction, 45 degrees above the plus x-axis. So that's actually the answers to part 2 of this. But then I also want to express this force in terms of in vector notation. So that's going to be 1 times 10 to the minus 14. That's the magnitude times cosine of 45 in the I direction, plus 1 times 10 to the minus 14 times sine of 45 in the j direction. And cosine 45 equals sine of 45. This works out to be 7.1 times 10 to the minus 15 I plus the same 7.1 times 10 to the minus 15 j newtons. And then that's the answer to the first part. Okay, now we're looking at number 2. I have 2 spheres of mass m, and then a third sphere of mass big M at the vertices of an equilateral triangle. A fourth mass m4 is at the center of the triangle. The net gravitational force on m4 from the other 3 spheres is 0. What is m in terms of m? All right, you might be able to just look at this and tell that the answer here, that the mass big M must be the same as the masses little m. But let me show you a little more rigorous proof of this. That if this is an equilateral right triangle, first thing I know is that this distance is equivalent to this distance is equivalent to this distance. So those distances are all the same. And then further, I also know that this angle is 30 degrees. And then if I draw my x and y axis on here, there's my x-axis. There's my y-axis. Then I also know that this angle is 30 degrees and this angle is 30 degrees. Let me just clarify this. So I know that this angle is 30 degrees because this angle is 60 degrees. And I know that that line splits those 2 angles equally. All right, I also know that if I were to draw my vector diagram, it is going to look like this. I'm going to have one force up, one force like that, and then one force like that. All right, now let's just draw this vector diagram. I have let's see, I'll just call this F2. This one is an identical force to F2 because these masses are the same. I'll call that one F2. And then this one I'm going to call F1 because it's potentially different. All right, and these angles are 30 degrees. Now, I know that the net force is 0. Now, I can look at this and tell that the x components of these 2 forces are going to cancel out because those are forces of identical magnitude and they're at the same angle. So when I take the x components of those, they're going to be equal and opposite. Now, let's look at the y components. I'm just going to draw the y components here of the forces. Here I have F1, and then down here I have twice of F2 sine of 30 degrees. The reason it's twice is because there's 2 of them. All right, and then if I simplify this, 2 times sine of 30 is just equal to 1, so I have F2. So from this, in order for there to be 0 acceleration, the net force to be 0, I know that the sum of the forces equals 0. That is that F1 minus F2 equals 0, so F1 equals F2. And if that's the case, if F1 equals F2, that means that these masses, get rid of these lines here, it means that all the masses have to be the same. So if F1 is equal to F2, that means that this mass equals this mass equals this mass. So the answer then for part A, see, I asked what is M in terms of M. The answer to that for part A is that M, big M, is equal to little m. And then also, part B should follow pretty quickly, that if we double the value of M4, what is the magnitude of the net gravitational force on the central sphere? Well, doubling this value is going to affect all of these vectors exactly the same. They're just going to all get bigger by a factor of 2. So the net force after doubling those two vectors by a factor of 4 doubling that, my net force is still going to be 0. Now let's see, problem 3 had to do with Newton's shell theorem. That is that a shell of mass, if you're standing outside a shell of mass, then it's the same, the gravitational force is the same as if it was a point mass. So here I just want to know, express the gravitational force on a particle at various distances, A, B, and C meters. So part A, I just treat all of this, actually I'm going to start with C. No, I'll start with A. Never mind, sorry. Start with part A. The force is equal to G times whatever the mass is, this particle of mass, M, times M1 plus M2 divided by A squared. All right, I'll just treat whatever mass is inside that shell, like I imagine whatever mass is inside this radius as a point source. And then similarly, as you might guess, part B, this is going to be G times M times whatever mass is inside this radius, M2, divided by B squared. And then C, when I'm in here, there's no mass inside of this point, inside of the radius C, so F is equal to 0. So kind of a cool thought experiment to do is say, well, what if our planet, the planet Earth, was hollow in the middle? Then there would be no gravitational field inside the middle of the Earth, and you could just go in there, you just float around, and be like you're in space, like you're with no effects of gravity at all. That if our planet was actually hollow in the middle, which is not, but if it was, then there would be no gravitational field. All right, let's see. What altitude above the Earth is the acceleration due to gravity equal to 5 meters per second squared? Well, we know, F equals ma, and F equals g mm over r squared. So if we put these two together as we did in class, we say ma equals g mm over r squared, and our masses cancel. We get this expression for A, and we can calculate this. But now instead of A being 10, as it is on the surface of the planet, it's going to be 5 meters per second squared. Our gravitational constant. The mass of the Earth equals 6 times 10 to the 24 kilograms. These aren't numbers you have to know. I would give them to you if you need them. The radius of the Earth is 6.4 million meters. All right, so that's 6 times 10 to the 24. Divided by, let's see, the radius of our planet Earth plus whatever height we're going to, whatever our altitude is. Because, like if this is the Earth, we want to know at what point h above the Earth is the acceleration due to gravity equal to 5. But then don't forget, you also have this radius of the Earth that you're actually accounting for. So when you're on the surface of the Earth, that r is equal to the radius of the Earth. But when you're at some altitude h above the surface of the Earth, then that r is equal to the radius of the Earth plus whatever your altitude is. All right, so now it's really just a matter of solving for h. It's probably easier to solve for the radius of the Earth plus h first. And let's see, we find that to be 8.9 times 10 to the 6 meters. I'll leave you to do that. But basically you're taking this value and dividing it by 5, and then taking the square root. And then we can solve then for h, subtracting the radius of the Earth, this 6.4 times 10 to the 6 meters, and I get 2.5 times 10 to the 6. All right, so that is h. Let's see, what will an object weigh on the moon's surface if it weighs 100 newtons on Earth? Okay, well, you probably know that the acceleration due to gravity on the moon is 1/6 that on the Earth. So this is on the moon, but we didn't want to show that. All right, so first of all, we want to just figure out what is the mass of this object. So I say that F is equal to mg. We say that F is equal to mg. Sorry about that. Hold on. Say F equals mg, and then I know that this is 100 newtons equals m times 10 meters per second squared. That's my acceleration on the surface of the Earth. So m here is equal to 10 kilograms. That's my actual mass. If it has 100 newtons on the surface of the Earth, then it'll have a mass of 10 kilograms. All right, so now I want to know what is its weight on the moon's surface. Let's see, the weight on the moon's surface. The weight on the moon's surface, we want to, we can just calculate from Newton's universal law of gravitation, g, the mass of the moon, the mass of our object, this m right here is for the moon, divided by r of the moon squared. And then I can put in some values here. The mass, or let's see, g is 6.67 times 10 to the minus 11. The mass of the moon is 7.35 times 10 to the 22 kilograms. Excuse me. 7.35 times 10 to the 22 kilograms times the mass of my object, which is 10 kilograms. So see, I'm just calculating now what is the force between this object and the moon. And then the radius of the moon is 1.7 million meters, 1.7 times 10 to the 6 meters. I want to square that value, and it gives me the weight, which is 17 newtons. But you know, if we know this whole thing about the acceleration due to gravity on the moon is 1/6 of that on the Earth, then I could just say that the weight on the moon is equal to 100 divided by 6, which is 17 newtons. All right, but this is really the way that we get to that value. And if I ask you such a question on a test, I'll expect you to actually, show me that. How many Earth radii must the same object be from the center of the Earth is weighed the same as it does on the moon? So here, I want to know how far away must it be on the Earth if it weighs the same amount on the moon? All right, so what I'm saying is F is equal to G mass of the Earth, mass of my object, which I know to be 10 kilograms, divided by the radius of the Earth. Or excuse me, the radius, not the radius of the Earth, squared. All right, so I want this force to be 17 newtons. I want it to be the same as it is on the moon, 6.67 times 10. The mass of the Earth is 6 times 10 to the 24. The mass of my object is 10 kilograms divided by r squared. At what height above the Earth does a 10 kilogram object weigh 17 newtons? That's what I'm asking here. And r turns out to be 1.5 times 10 to the 7th newtons, or meters rather, 15 million meters. And then if I want to know how many Earth radii that is, I just divide it by the Earth's radius. So 1.5 times 10 to the 7th meters divided by the radius of the Earth, 6.4 times 10 to the 6 meters. And that's equal to 2.3 Earth radii. So it has to be almost 2.5 times the radius of the Earth away from the Earth in order for it to have the same weight as it would on the Moon. All right, the mean diameters of Mars and Earth are 6,900 and 13,000 kilometers respectively. The mass of Mars is 0.11 times the mass of Earth. What is the ratio between the mean density of Mars to that of Earth? All right, so part A, I want to know what is the density of Mars versus the density of Earth. Or to use the symbols for the planets. The symbol for Mars looks like this. The symbol for Earth I've already used looks like this. So I want to know, density is just mass over volume. Or I can rewrite this. Mass of Mars, volume of Earth, over mass of Earth, volume of Mars. And then I know these ratios pretty simply. The mass of Mars is 0.11 mass of the Earth. That was given in the problem. Over mass of the Earth. And then the volume of a sphere is 4/3 pi times the diameter over 2. That's the radius squared. You don't really need to know that because you know that the volume is proportional to the diameter cubed. So then I'm just going to write the diameter of Earth over the diameter of Mars cubed. So the diameter of Earth cubed over the diameter of Mars cubed. All right, what I've done here is I've substituted this in for the volume, but then I've canceled out the 4/3, the pi, and the 1/2 squared out of each. So I'm just left with the diameter cubed. Okay, and let's see, this cancels. I know the diameter of Earth, and I know the diameter of Mars. Those are given in the problem, and I find this to be 0.74. So that is the ratio of the mean density. And then what is the value of the gravitational acceleration on Mars, and what is the escape speed on Mars? Well, I've already shown that G is gm over r squared. But here we're just using the radius of Mars, the mass of Mars, which we have those values. It's 6.67 times 0.11 times the mass of the Earth, which is a number that I've already given you, 6 times 10 to the 24. Again, not a number you need to know, one I'll give to you. Divided by the radius, let's see, 6,900 kilometers, which is 6.9 times 10 to the 6th, divided by 2, because I need to get the radius, squared. And that gives me an acceleration on Mars of 3.7. So a little less than half that of the acceleration due to gravity on the surface of the planet Earth. All right, let's see. C, I also want to know the escape speed on Mars. Just for reference, the escape speed on the planet Earth is equal to 11,000 meters per second. That's how fast you have to kick a rocket up into the air to escape from the Earth's gravitational field. Again, as we said in class, actually, when they launch rockets, they actually go with the rotation of the Earth. So it's not just the speed of the rocket that has to be this, but it's the speed of the rocket plus the speed that's given by the rotation of the Earth. So 11,000 meters per second. The escape speed is the square root of 2gm over r. So that's 2 m is 0.11 times the mass of the Earth. Divided by the radius. It's not squared, it's just the radius. And then that's equal to 5,000 meters per second. So to take off from the surface of Mars, you have to have a speed that's roughly half that you have to take off from the surface of the Earth. Let's see, I think that was the end of that problem. Just a few more problems. All right, this next problem, I want to find the gravitational potential energy of the system of particles. We're going to have very similar problems when we get into charges and potential energy. To do this, you want to figure what is the gravitational potential energy of these two particles, and these two particles. And then I just add them up. So I'm going to call those U1, U2, and U3. U is equal to U1 plus U2 plus U3. If you remember, U is equal to G mm over R. We derived this in class, but I'll just give it to you here. And so that's going to be, well, the masses are all the same. The radii are all the same. So it's just going to be 3 times G mm over R. Because each of these are all 2 kilograms. Now, if they weren't all the same, like if these two are different, then you would have to add up the separate components. Like you have to work this out longhand. But all the masses here are the same, so it's a pretty simple calculation. So that's 3, because they're all the same, 6.67. See, the masses were each 2 kilograms. Divided by the distance, which was 3 meters. I get 2.7, 10 to the minus 10 joules. Not a lot of energy, but the gravitational force between, just sort of regular objects is very small. But we'll see with electrical forces that there's a lot more energy contained within electrical charges. Those forces are a lot bigger than you see with gravity. And it works out exactly the same. So we'll see this again soon, I think in one chapter. All right, so we consider in the universe a flat structure that's 100 parsecs by 100 parsecs. A parsec is 3 times 10 to the 16 meters, by the way. That has a mass 1 million times the mass of the sun. What is the gravitational field at a distance of 1 parsec above this flat structure? And then 100 parsecs from the mass. So if you remember from Gauss's law, the flux is equal to negative 4 pi g times the mass inside my Gaussian surface. All right, so if I have a flat structure, if I have this flat sheet, all right, this is my flat sheet. It has an area of 100 parsecs by 100 parsecs and a mass, 1 million solar masses. So this is like some huge structure like out in the universe. And then if I imagine I draw a Gaussian surface, let's see if I can draw this. On this Gaussian surface, I have one part above the sheet. And then I have another part below the sheet. I'll draw that. The below part I'm going to draw, let's see, in green. All right, so I have one Gaussian surface on the top and one on the bottom, and the flux is just, the sum of all the flux that's going through all of these, through these two surfaces. Okay, so remember my flux is really just G, which is my gravitational field, times the area of my Gaussian surface, and this is going to equal negative 4 pi G times the mass inside. Now, I want to know what am I looking for? The gravitational field. So I'm looking for G. We've called this gravitational acceleration in the past. We're going to call it the gravitational field now, but it's the same thing. So I'm looking for G. So this is negative 4 pi g, the mass that's inside my Gaussian surface that I've constructed, which is the total mass of the object, divided by the area, which in this case is going to be twice the area of the sheet. So this sheet has an area A, this sheet has an area A. So my Gaussian surface has a total area of 2A. We derived this in class, and this is for a sheet. It's different if it's a sphere, it's different if it's a cylinder, and both of those were in your notes, so you should be aware of all of them. But this is the basic idea of Gauss's law, that the flux, the total flux, is equal to negative 4 pi times g times the mass inside that Gaussian surface. Okay, so now I can put in some numbers, negative 4 pi the mass inside, well, how much was it? A million solar masses. A solar mass is, one solar mass is 2 times 10 to the 30 kilograms. So this is 1 times 10 to the 6, that's a million, times 2 times 10 to the 30, and that's a million solar masses, divided by twice the area, 2 times 3 times 10 to the 16, that's a parsec squared. And then 2 because, again, we have 2 flat surfaces over here that we're measuring flux through. And then if we do that, we get G. I get 9.3 times 10 to the minus 7 meters per second squared. Or, you know, I'm going to express this in a slightly different unit, for reasons that we'll see in a later chapter, because we'll express an electrical field in this way. But I'm going to express it as 9.3 times 10 to the minus 7 newtons per kilogram. So this field, this gravitational field, is a measure of force per unit mass. Force per unit mass. Later when we get into electricity, we'll see that the electric field is a measure of force per unit charge. And that doesn't seem like a very big force, but while this is a very massive structure, it's also spread over a very large area. So and then part B is going to be exactly the same. My G will be 9.3 times 10 to the minus 7 newtons per kilogram. Remember, for the flat surface, the acceleration due to gravity, or the gravitational field, was not dependent upon the surface or on the distance from the mass. That was not true for spheres and cylinders. It was dependent upon the distance, but not here with a flat structure. I think this is the last one. What is the gravitational flux emanating from the Earth? Okay, well, flux is my Greek letter phi, whatever. And we know from Gauss's law, this, by the way, remember, is roughly speaking, it's G, my gravitational field, times the area where I'm measuring this flux, right? So like if I want to know the total flux emanating from the surface of the Earth or from the planet Earth, I want a spherical Gaussian surface that goes around the entire planet. So it's G times the area is my flux. And I know from Gauss's law that this is negative 4 pi times G times M. And I've already given the mass of the Earth before, 6 times 10 to the 24 kilograms. And that's it. And this comes out to be 5 times 10 to the 15. And the units of this turn out to be meters cubed per second squared. Actually, I'm going to write it first as meters per second squared times meters squared. Remember, G times area. R, we can simplify this as meters cubed per second squared. But our flux is just a measurement of our gravitational field, our gravitational acceleration, times the area of this surface through which you're measuring the flux. We're going to get into flux a bit more in the next chapter on electric fields, and we'll use a lot of the same things that we've done here for that. I do believe that's the end. Yeah.